Okay, so now we're ready to talk about probably one of the most important concepts in statistics. In 12.4, we're going to cover the normal distribution. It turns out that a great many things can be modeled by the normal distribution, and it tells us a lot about what is going on with the data and the population that we're interested in. So we have quite a few objectives, but not really a lot of slides, right? So the slides are really dense today. What we want to do is recognize the characteristics of normal distributions. We want to understand the 68, 95, 99.7 rule. This is huge. I think that if we're talking about normal distributions, which is probably one of the most important things in statistics, probably one of the most important things to understand about the normal distribution is the 68, 95, 97 rule, okay? From that, we're going to find scores at specified number of standard deviations from the mean, and this is what we're going to call our z-score, and this is going to tell us how far away a data point is from the center. We're going to use the 68, 95, 97.7 rule along with the z-scores to be able to tell us some things about the population, okay? We want us to understand the percentiles, right? This is actually 68%, 95%, 99.7% of the data. And the quartiles. The quartiles is probably less important. And then we want to use and interpret margins of error. Margins of error is, again, another very important thing. That's one of those things that you always see below the polls and in magazines and in news articles and stuff. And so how do they get a margin of error? What's a big enough sample size? And then in our very last slide, we're going to recognize distributions that are not normal, okay? Because not everything is normal, but a lot of things are, all right? So what is the normal distribution? Okay, so the normal distribution is called the bell curve, or also the Gaussian distribution. And the normal distribution is bell-shaped and symmetric about a vertical line through its center, such that the mean, median, and mode are all equal and located at the center of the distribution. So if I have a height of a random sample of 100 men, what happens is I got a little extra hump over here, and it's a little bit shorter over here for the 100 men. But it piles up toward a center, and it comes back down. So here the mean, median, and mode are all very close together. So what I do is I increase the sample size, and now you'll notice that as I increase the sample size, there's something that happens. It's starting to even out and look more and more symmetric, and as the sample size continues to increase, the left and the right hand side are basically symmetric with each other about this center of distribution here, where the mean, median, and mode start to converge on the exact same point until we get a normal distribution for the population, which is this smooth symmetric curve where the mean, median, and mode are the exact same value. And so we can say that this is approximately normal, this is approximately normal, this is approximately normal, and then this is normal. So I can impose a lot of the characteristics of the normal distribution on a lot of normal looking data so that I can tell things about it. And that's the real power of the normal distribution, right? And so the shape of the normal distribution depends on the amount of variation. I'm sorry, I'm having a hard time grabbing the slide. All right, so the mean, median, and mode are all in the same place, but this one has very little spread. Okay, so maybe this is like iPhone cases over here, and the fit of iPhone cases is very close, right? Because if it's too small, it won't fit on, and if it's too big, it keeps falling off. So the tolerances are very tight. Okay, and then maybe we have something that is less strict, a little bit more variable over here, and then maybe we have something that's really varies over here, like the height of adult males. Okay, so which would vary from, maybe slightly less than 4 feet, all the way up to almost 10 feet, for certain basketball players and stuff. So you got a real extreme of heights here. All right, so but the mean, median, and mode are all in the same place for the entire population. So the shape of the normal distribution depends on the mean and the standard deviation, how much variation there is. These three graphs have the same mean but different standard deviations. As the standard deviation increases, the distribution becomes more spread out. So the mean, median, and mode are in the same place, but the standard deviation is getting larger and larger for each one of these because we have more and more variability in our data. It turns out, though, that the standard deviation is picked such that this is what happens with our normal distributions, right? Approximately 68% of the data items will fall within one standard deviation of the mean in both directions because it's symmetric, right? So as I go this way, this represents about 34% of the data from 0 to positive 1, and from 0 to negative 1 represents the other 34%, so that I get 68% of the data in between negative 1 and 1 standard deviation of the normal distribution. If I go from negative 2 to 2, I actually hit 95% of the data items, approximately, right? Because if there's a little bit of skew in the data, it won't quite work out that way. But for perfectly normal data, 2 standard distributions gives us 95% of the data. That means that there's only 2.5% in this tail over here, and 2.5% of data in this tail over here. Alright, and then once you get out to 3 standard deviations, you're talking about 99.7% of the data, or less than about 0.15% of data is in these tails over here. So that's pretty tiny, okay? But that's what we've got for the standard deviation. So 1, 2, and 3 standard deviations, 1, 2, and 3 standard deviations of a normal distribution. Remember, this is a normal distribution. Is going to follow this 68, 95, 99.7 rule. Okay, and we're going to use this as a ruler for our variability within the data. Okay. Now, if we're going to use this for the variability within our data, we need to, play around with this. So, male adult heights in North America are approximately normally distributed with a mean of 70. So, my mean is 70. And remember, X bar here means mean. Okay. And a standard deviation of 4 inches. So, my standard deviation is going to be 4 inches. Find the height that is 2 standard deviations above the mean. Okay, so above means add the mean. Okay, so 2 standard deviations above the mean. So here's 2 standard deviations above the mean. And that's going to give you 78. Alright, so 78 inches is 2 standard deviations above the mean. And hopefully that makes sense because this is 6'6". And you would not expect to see a whole lot of people above 6'6", because you're talking about less than 1%, 1.5% of the population is going to be taller than that. Right? Now, what if we actually want to use the 68, 95, 99 rule? Use the distribution of male adult heights in the figure to find the percentage of men in North America with heights between 66 inches and 74 inches. Well, look, my 66 inches is right here. My 74 inches is right here. That's 1 standard deviation above and below. And so that's going to be 68% of the heights. So 68% of North American men are going to be between, 72 is 6 feet, right? So you're going to have 5'6" to 6'2". So between 5'6" and 6'2". And I think you can probably agree that most guys are not shorter than 5'6", and most guys are not taller than 6'2", and that's going to account for about 7 out of every 10 guys. Now, the 68, 95, 97 rule is great when we know even numbers of standard deviations, but some data is not going to be 1, 2, or 3 standard deviations away. It's going to be a varying amount of standard deviations away, right? So what are we going to do with that? Well, now what we're talking about is computing a z-score, okay? So if I'm computing z-scores, a z-score describes how many standard deviations a data item in a normal distribution lies above or below the mean. The z-score can be attained by using the following formula right here, right? You're going to take the data item that you're interested in and subtract the mean, and then divide by the standard deviation, and that gives you your z-score. This is really important because what we're doing is we're changing the data item into a distance away from the center, where a positive z-score means you're above the mean, and how far above the mean. 1, 2, 3 standard deviations. If you're less than 1 standard deviation above the mean, you're not very far away from the center. If you're 3 standard deviations above the mean, you are really far from the center. That's an extreme value. And of course, a negative is going to mean below the mean, right? And then of course, the further away you are from 0, the more extreme the value is, right? So how does this work? Well, we're going to have an example here. If I can grab it. So here's my example. Let us try to calculate the mean weight of newborn infants is 7 pounds and the standard deviation is 0.8 pounds. Okay? The weight of a newborn infant are normally distributed. Find the z-score for a weight of 9 pounds. You're like, oh, okay, so 9 pounds. Well, 9 pounds doesn't fit on this chart, right? I mean, we're looking at 7.8, 8.6, 9.4. I don't know how many standard deviations that is, unless I use my z-score calculation, right? So how am I going to figure out exactly where it goes? I'm going to take the 9 minus the 7 and divide it by the 0.8. And of course, if I grab my handy dandy calculator and type that in, I get 2.5 standard deviations, and because it's positive, we're above, and so we're right here at 2.5 standard deviations above the mean. Well, is that kind of an extreme value? Well, it's between 95 and 99.7% above. So you have to remember that this is going to include this tail right here is 2.5% of all of the data values, right? So that means that what's below this, that most children are going to be, what, 97.5%. This is going to represent right here, 97.5% of all births are going to be less than 8.6. I'm above that. So I would say, probably. This is probably kind of an extreme value, 9 pounds. Now, I happen to be 9 pounds, but that's toward the extreme. Most of my daughters in the 7 pound range. So they were about average. Now, this one requires a little bit more algebra because we're working backwards. Okay? So, we have an IQ test. The Stanford-Binet intelligence tests are normally distributed with a mean of 100 and a standard deviation of 16. What is the IQ corresponding to a z-score of negative 1.5? Well, let's say we know how far away from the center we want to be, okay? Let's say that negative 1.5 is some sort of cutoff for psychologists. It gives us a nice percentage to figure out maybe where certain learning disabilities occur or certain cognitive deficits occur. And so you're like, oh, well, now I got to go backwards, right? So remember, the z-score is equal to the data minus the mean all over the standard deviation. Well, I know the z-score, that's negative 1.5. I'm looking for the data value. I'm going to call that D. I know what the mean is, it's 100. And I know what the standard deviation is, it's 16. Now, because we're solving for the data, and that's the only solving we're ever going to do, we can actually do this by just a step-by-step process. So you can always now multiply, you can still see that, right, by the standard deviation. Okay, so I'm going to multiply 16 times negative 1.5. Right, so multiply by 16, multiply by 16, those guys will reduce. And so now I'm going to have negative 24 is equal to D minus 100. And so now hopefully you know that the next step to do here is to add, and it'll always be add the mean, and we're going to do that to both sides. So I'm going to add 100 and add 100, and of course these cancel out, and I'm left with the data value is equal to 100 minus 24 is 76, right? And so you have 76 is the IQ score that's negative 1.5 standard deviations below. Alright, so just follow those two steps and you'll always get the data value that you want. Alright, great. This is in here, I guess I just want to talk about this briefly. 25% of the data does not correspond to any nice standard deviations, but what I would like you to notice is that 50% of the data falls very, very close to the center because it's very, very tall. And then the wings, the other 25%, is much, much longer, much, much wider, because you can see it drops down so fast. So this is about the same amount of area. This right here, let me draw it. Right. This right here is the exact same amount of area as this is right here. It's just this is really tall and this drops off and gets really short really quickly. Okay, so you got a real cluster of half of the data is very close to the center, and then because the tails fall off very rapidly, the other two 25% are just very wide. Okay. We are almost done. Okay, a percentile interpretation for z-scores. Using the z-score in a table, you can find the percentage of data items that are less than any other item in a normal distribution. You can also use your TI calculator. You can use the TI 84 calculator for this. Alright, and this is something we do a lot in stat methods. Alright, so I don't know how much people use tables anymore, but I don't use them at all. In a normal distribution, the mean, median, and mode all have a corresponding z-score of 0 because they're right in the center. And that means that they are in the 50th percentile. Thus, half the data is below and half the data is above, which makes sense, right? Because these are all measures of center. Now remember, we had 8 objectives, and we're down to the last couple, okay? So now we're talking about poles and margins of error. Statisticians use properties of the normal distribution to estimate the probability that a result obtained from a single sample reflects what is truly happening. If n is the sample size, there's a 95% probability that it lies within 1 over the square root of n of the true population statistic. Now, there's a bunch of proof for this. And it's really long and really involved, and I don't know that anybody really watching this video cares. If you do, you can probably find some great stuff on MIT's Open Course. But this is basically what happens. With a 95% probability, we know that this is true. And so we're going to call this the margin of error. How far away are we from what we feel like the true population statistic is? Because remember, we're only taking a sample, and that sample has variability to it. And so while I am going to get a mean or a proportion from my sample, I can't be 100% sure that that's the actual true value of the population because I only took a small sample, and samples vary. So this is going to be my margin of error, plus or minus 1 over the square root of n times 100. Alright? So, how do I get a margin of error? Well, let's say that in a random sample of 1,172 children, ages 6 through 14, 17% of the children said getting bossed around is a bad thing about being a kid. So, these are children, they're getting bullied in elementary and middle school, and they said that this is one of the bad things about being a kid because it happens to so many of them. So we want to verify the margin of error. Well, if we wanted to be 95% sure, and we don't have a formula for anything else, then we want to put 1 over the square root of n. Now remember, our sample size here is the 1,172 children, so I'm going to have 1,172 is equal to what? Oh, times the 100%. Got to convert it, right? Times the 100%. Well, let's go ahead and do that in our handy TI-89 calculator, right? So we have 1 over second, the little squared button, 1172. I have the new operating system, so I'm going to right arrow out. If you don't have the new operating system, you do have to put the parentheses in. That'll be really important. And then I'm going to multiply that value by 100, and I get 2.92%, right? So I'm going to have 2.92%. So this 17% statistic, I'm going to scroll this up just a little bit. That 17% statistic that we got from the sample, with a margin of error, that means that if I add basically 3%, let's just go ahead and round that to 3%. If I add 3% to that, then I'm going to get 20%. And if I subtract 3%, let me not do it this way. If I subtract 3% from it, I'm going to get a value that is 14%. And so what we're saying is while the sample gave us a center of 17, I'm basically 95% sure that the actual value is between 14 and 20%. Okay? That's what I'm 95% sure of. It's kind of squishy. It could actually be lower or higher, but that would mean that my sample was pretty extreme, and so I'm 95% sure that the actual value is between 14% and 20%. That children said getting bossed around is a bad thing about being a kid. Okay? So that was what we were measuring. Getting bossed around is a bad thing about being a kid. That's what we're 95% sure the actual value is between 14 and 20%. That children think that getting bossed around is a bad thing about being a kid. Oh, you couldn't see that, sorry. So there it is. Okay? Now we've only talked about normal distributions. This is our last slide. This is our last topic. There are other kinds of distributions. This graph represents a population distribution of weekly earnings in the United States. And so because there is a lower limit, you can't make less than $0 in a week, but there's no upper limit on what people can make. There are relatively few people with very high weekly incomes. Alright, so, you know, we're over here in LeBron James, Warren Buffett territory over here. Alright, and so the mean, median, and mode are not the same. They're being dragged over to the right by these extremely high values over here. And so what happens is the most frequent income, the mode, occurs toward the low end, and so and the mean gets dragged up toward the high end, and the median always stays in between. So the median is less sensitive than the mean to where the center is. So when we have these skewed distributions, we like to talk about the median and the interquartile range more than we like to talk about the mean and the standard deviation. This is one of the problems with trying to curve grades. because even though you do have an upper limit of 100 and a lower limit of 0, really what happens is you get some people in the 50, 55 that just barely failed, and then you may have people who earn like 20s, okay, who abysmally failed. And then you get the opposite direction of this tail. You get something that looks like, oops, this, where you got a few people who scored really well, and then you have some crazy stuff that happens over here. And so this is called skewed. Alright, this is a skewed distribution because a large number of the data ions are piled up at one end or the other, with a tail at the other end. And so the tail is pulling it from being symmetric. So this is right skewed because the tail is pulled to the right. This is left skewed because it is pulled to the left. Alright, thank you for watching this video on the normal distribution. I hope you enjoyed it, and stay tuned for some more videos.